Welcome back, guys. Today we're going to be taking a look at problem 2 of the 2019 USAMO. My motivation for making this video today was that I was doing it earlier and I found that the solutions online, there were only two of them. One made use of symmedians and the other of inversion. And when I was doing this problem, I found a solution myself which only made use of simple concepts like angle chasing and lines and circles and all that stuff, so I wanted to share that with you guys here today. Now, the problem here says that ABCD is a cyclic quadrilateral satisfying AD squared plus BC squared is equal to AB squared. The diagonals of ABCD intersect at E. Let P be a point on side AB satisfying angle APD is equal to angle BPC. And we want to show that the line PE bisects CD. We're actually going to do something a little different this time in drawing the figure. Instead of just drawing our regular cyclic quadrilateral ABCD and trying to make sure that the condition AD squared plus BC squared equals AB squared holds, we can actually think about this another way. First of all, the condition reminds us of Pythagorean's theorem. In other words, we can construct a triangle with side lengths AB, AD, and BC, and it should be a right triangle with the right angle opposite of length AB. So what we can do here is we will first draw the circumcircle and AB forming a chord, and then we're going to draw a circle whose diameter is AB. So this means that any point on the circle will form a right angle with the points AB, or also a right triangle. So by our condition, AD and BC should correspond to two chords on this circle. So we can first draw a circle centered at A passing through our point D, and then we let the intersection be, it's C right now, but I'll rename it X later. So we have this intersection, and then we draw a circle centered at B with the radius to the intersection, and then that circle will intersect our original circumcircle at point C. So this works because we know that angle AXB is 90 degrees, and AX equals AD, BX equals BC, so we have that AD squared plus BC squared is AX squared plus BX squared, which is AB squared since AXB is a right angle. Okay, so now we have found another way to draw our cyclic quadrilateral, so that's pretty nice. So we can finish off the remaining construction, which is let's connect AC and BD, let the intersection be E, and then we can also plot the midpoint of side DC, and we call that M, or we can call it F here because I don't want to rename it. And then we can finally draw the point P, which is on line AB, such that angle APD equals angle BPC. Alright, so we can now proceed to actually solving the problem. And the first step in the solution is to notice that P seems to lie on this line. The only way we can make these kinds of guesses is to draw a nice and accurate figure, which is exactly why drawing a nice figure is so important. When I was solving this problem, I drew a pretty accurate figure, and I was just like, wait, maybe P lies on this line. So these hypotheses are actually really what helps us propel towards our solution. And so we might want to prove that later, but let's first call the intersection between this line and AB, let's call this point Q. Later we might want to prove that P equals Q. And as it turns out, this hypothesis is actually correct, so we indeed want to prove this. And after that, we will want to prove that Q, E, and F are collinear. Well, why is that? If we prove that P equals Q and QEF are collinear, then we prove that PEF are collinear. And since F is the midpoint of DC, indeed we will prove that PE bisects CD. So we will solve the problem if we prove these two things. Now then, let's work on proving these two things, starting with the first one, P equals Q. Well, we need to notice something interesting about Q first. So Q lies on this line, which means that Q has equal powers to this circle, and this circle. The reason being, these three circles intersect at exactly these 2 points, so their radical axis is just this line, and anything lying on that line will have equal powers to them three. Also, Q lies on line AB, which is a radical axis between this, I have the wrong color, between this circle and this circle. So, Q also has equal powers to these two circles. And since this circle, Q has equal powers to this circle, this circle, this circle, Q has equal powers to all four circles. It is the radical center of these four circles. So, we also have the condition that APD is equal to BPC. If we slide P along the line AB, if we slide it across this way, APD will increase and BPC will decrease. Sorry, APD will decrease and BPC will increase. If we slide it the other way, the other thing will happen. So there's only exactly one point P on AB such that APD equals BPC. What this means for us is that if we can prove that angle AQD is equal to angle BPC, we will have indeed proved that P equals Q because P is unique on this line. So if Q satisfies the same condition, Q is P. So we just want to prove this. And what we can do here is to prove that these two angles are the same, we can look at these triangles and these two angles. So it is equivalent to prove that this angle plus this angle equals this angle plus this angle, since they're part of a triangle. Okay, so we know what one of these angles are. For example, DAB is just corresponding to the arc BD, the major arc BD. So we just want to prove that the major arc BD plus whatever this angle is, let's just leave it blank for now, is equal to this angle is the major arc AC plus whatever that angle is. I'll also leave it blank. And now we want to find what this angle is. Well, how do we do that? If we extend this over a bit, it seems that it maybe is the intersection of these two circles. Well, indeed, we will see that this is true. Why is that? Since Q lies on the since Q is the radical center of all four circles, it must have equal powers to this circle and this circle. So Q must lie on the radical axis of these two circles. And the radical axis is exactly this line where this is the intersection. Hence, if we extend this, it will indeed intersect there at the intersection. So we know that this angle is actually just equal to this angle. This angle, let me maybe mark it in red so it's easier for you to see, is equal to this angle. Because AD and this is an isosceles triangle, so this angle equals this angle. And this angle, we know exactly what that is. That is the minor arc AD. So we can put that here. We can make the exact same argument on that side to show that CQ extended meets this point here. So this angle is this angle, which is arc BC. Okay, we get this that we want to prove. If we prove this, then P equals Q. Major arc BD plus minor arc AD is just major arc AB. And major arc AC plus minor arc BC is also AB. So these two are indeed the same, and we have shown that P equals Q. So we can now just move on to the second step because we've proved the first one, which is to prove that QEF are collinear. Since we proved P equals Q, I'll just use point P from now on. We know that P lies on this line, and I just won't need Q anymore. We want to prove that P, F are collinear. So how do we do that? Well, we know F is the midpoint, and one way we can make use of the midpoint condition is to obviously show that, or not show, we can make use of the fact that DF equals FC. So that reminds us of CEVAs. If we draw out these two lines, and then we label the intersection between this line and AC, and this line and DB, then we want to prove that the lines CA, DB, and PF are concurrent. And by the way, let me label these points or give them some names. So we want to prove that CK, DL, and PF are concurrent, specifically at E. Well, E doesn't really matter, but we want to prove that these three lines are concurrent, so we can apply CEVAs, which means we want to show that PK over KD times DF over FC times CL over LP is equal to 1. But DF is equal to FC, so this is just 1, and we can just write it out. So we just want to show that PK over KD is equal to LP over CL. PK over KD is equal to LP over CL. And that is essentially just the same as showing that the line KL and DC are parallel. So our second thing that we want to prove is just the same as showing that KL and DC are parallel. So we might think to explore some other conditions to prove that they are parallel, but we can actually see that it is better for us just to try to prove that PK over KD is equal to PL over LC. Well, why is that? Because we can look at this triangle right here. PK over KD, we know from law of sines, this length is, actually I need some names first. I don't need names. So we know that PK over KD from law of sines is just equal to sine of angle PAK, which is just PAC, over sine of angle CAD, which is KAD, multiplied by AP over AD. I think this should be true. Yes, this is true indeed. And we can do the same thing for the other side, but it's the same thing, so I won't go in depth in the explanation. We should just have a very symmetrical expression here times BP over BC, and we want to show that these two values are the same. So there are actually some things we can cancel out here. First of all, CAD is just equal to DBC, which is this. So we can cancel out these two, and we just want to show that these two things are the same. And we can actually do something about sine PAC and sine, wait, this is not, I don't know why I wrote BPB. This should be sine of, if we want it to be symmetric, this is just sine PBC. And we know that PAC is just BAC, which corresponds to side BC, and this thing corresponds to side AD, because they lie on the same circle and they subtend the two arcs. Okay, so now if we can move these things over, we essentially just want to prove that AP over AD squared is equal to BP over BC squared. Okay, so how do we prove that this is indeed true? Well, what we can do is we can just move everything back up here. Since we know that AX equals AD, we can replace AD by AX to get AX squared, and similarly we can replace BC by BX squared. And here is, we want to prove that AP over AX squared is equal to BP over BX squared, and this actually just results from a bit of trigonometry. We know that this is a right angle, we know that this is a right angle, and whenever we have this configuration, it is actually just, this is just true, it turns out. Well, I didn't know that until this problem, but apparently it is. So let me label these things as theta. And we can actually express some of these things. For example, AP over AX is sine theta. So we can write down sine theta over AX. That will be the left-hand side. And BP over BX is cosine theta. So on the right-hand side, we have cosine theta over BP. And, BX. So we can move things over a bit. We get that we want to show sine theta over cosine theta is equal to AX over BX. By the way, this is just tangent theta. So we want to show that tangent theta is equal to AX over BX. And let's look at what that actually means in this triangle. AX, BX, tangent theta. But well, tangent theta is just defined as opposite over adjacent, which is just AX over BX. So this is obviously true. Okay, we have proved everything we wanted to, and this thing tells us that condition number 2, which is that QEF are collinear, is indeed true. In summary, we have shown that P equals Q and QEF are collinear, so indeed our PE bisects CD is true. And the most important takeaway for this problem is to guess at what this point P might be, because P is defined as such that these two angles are the same, but that doesn't really give us much to work with. Instead, we guess that P actually lies on this line, and we prove that, so we have more to work with.